Hello, I hope you're well. Today we are going to look at starting chapter 4. And chapter 4 is about inverse functions. So we introduced functions and operations on functions back in chapter 2 and 3 and back in chapter 2. And now we're going to look at inverse functions. So if you turn in your book, you can see here, let's see what page it is, on page 319 in your book, the definition of a function, an inverse function. So it says, let f be a function g is said to be the inverse function of f if the domain of g is equal to the range of f, and for every x in the domain of f and every y in the domain of g. This happens. Well, that's like, seems like a lot, right? So let's just turn it down. There is an inverse of a function if the function is considered one-to-one, meaning, you know how we learned the vertical line test to see if an equation was a function. Now, to see if there's an inverse function, if it's one-to-one, we're also going to look to see if it passes the horizontal line test. So let's go ahead and look here at some, right here on page 322. You can see these two graphs that we have up here. The one on the left is not a one-to-one function, because you can see that when you draw a line, a horizontal line left and right, it goes through two different points. So it looks like in two different inputs gives you the same output. So that's not considered a one-to-one function. It does pass the vertical line test, but not the horizontal line test. The graph on the right is one-to-one because it passes both the vertical and the horizontal line test. So if you go up to, so right here, for a function to have an inverse function, it has to be one-to-one. That is, if f of a equals f of b, then a equals b. So let's go back up to the mapping on page 320. So if you look at this mapping, it says that all of the inputs x that go into the function f come out of f of x, and then in the blue, and then all of the inverse inputs go into f of x and they come out into x. So from red to blue is going through the f function, from blue to red is going through the inverse function. Okay, and we can see this also by looking at a table of data of a function. So if you go to page 321, there's this table here right to the left of where it says one-to-one functions. This table here, you can see that a -2 goes to 4. And it doesn't, a -2 doesn't go to anything else. So it does qualify to be a function, but it's not a one-to-one function, because if you look at on the right-hand side, the right-hand column is going to be now the inputs for the inverse, if there were to be one. And this cannot have an inverse function because you can see that 4 on the right goes to -2, but also at the bottom 4 on the right also goes to a +2. So it's not a one-to-one function. Okay, so let's see. Okay, we're also going to use the instructions on page 321 to learn how to symbolically find the inverse function, but we're going to do that in a little bit. I'd first like to start with problems 13. Let's go back to our problems here. So if we go down to where the exercises start here on page 327, I'd like us to look, start with 13 and 15. So it says, verify that the given functions are inverses of each other. To do that, we are going to use so to verify that we have a given function are inverses of each other, we're going to use the composition that we learned back in chapter 2, I believe it was. And so if two functions are, when we compose them together, if they equal x, then that shows that they are inverses of each other. And I'm trying to get to that here in the book so you can see that. I think it's at the beginning of the lesson here. Right here. So on page 320 at the top, it says, if f is a function with an inverse f to the -1, so when -1 is your exponent of f of x, it means it's an inverse. That's what they're referring to. So if we compose f with its inverse and we get x at the end, and we do the same thing, we compose the inverse with f and we get x at the end, then we know that they are inverses of one another. So that's one way to verify. You can see here on page 320, there's an example. The function is f of x is 3x minus 4, and the function g of x is x over 3 plus 4 over 3. And so when we compose them, g goes into f as our first, when we're looking at here where my mouse is. So we're putting the g of x function in for the f function. And when we simplify, we get x. Then we do the same thing down below and we do g composed with f, means that f of x function is the input into the g function. So there in the numerator where x is, we put the function f of x, 3x minus 4. And when we simplify here, we also get x. So that means that f and g are inverses of one another. So let's go back down to our assignment for problems 13 and 15 here. So on 13, we have the function f of x is equal to a -3x plus 8, and then g of x is a -1/3 x plus 8/3. And we are going to show that f composed with g equals x, hopefully, and that g composed with f also equals x. And I will share my screen here. Okay. So we're going to do f of x composed with g of x. Okay, so that means that f is the g of x function is going to be the input into the f function. Okay, so my big overarching function is this -3 times something, and the something is my g of x function. That's the input now. Plus 8. So -3 times something plus 8 is my f function. And so when I simplify, that means I'm going to distribute this -3 to each of these pieces. We get a positive x minus 8 plus 8 at the end here. And so that -8 and the +8 cancel, and we're left with x. Now we want to compose the g of x function composed with the f of x function. So now g is my big function, and f of x is going to be the input into that. So my g function is a -1/3, and x is now my f of x function, so -3x plus 8 plus 8/3. So I have to distribute through this -1/3. That becomes a positive 3x/3 minus 8/3 plus this 8/3. And 3/3 cancels to make 1, and then a -8/3 plus 8/3 cancels out, and we're left with x. So yes, they're inverses of one another. So let's look at 15. 15 is giving us two functions, f of x and g of x. Go ahead and take a minute to write those down. And we are going to compose them together. So we are going to compose f composed with g of x. So f is the main function and g of x is going to go in for the input. So we have something cubed. That something cubed is my g of x function. And so I have x, the cubed root of x minus 2, which is the same as x minus 2 to the 1/3. That is the same as the cubed root. And that is to the power of 3 plus 2. And so that means we have x minus 2 to the 3/3, which just equals 1, plus 2. And so this is just x minus 2 plus 2, because this is x minus 2 to the 1. So combining like terms, minus 2 plus 2 adds to 0, and we're left with x. So f composed with g satisfies what we need. Now we need g composed with f. So g composed with f of x. So g is my big function. So the cubed root of something minus 2, and the something is my f function. So it's x cubed plus 2, and then subtracting 2. This is my f function right here. Goes in for x up here. So we have the cubed root of x cubed, because 2 minus 2 adds to 0. And so this is the same as x cubed to the 1/3. And that's x to the 3/3, which equals 1. So it's just x, which equals 1. So f of x and g of x are inverses of each other. Okay, so the next ones I would like to do are 19 and 21 in your book. And 19, let's just go ahead and look at the book right here. It's easier, I can write on this. So it says state whether each function can be given by a table is 1-to-1. Okay, so 19 and 21. So 19, how I would look at this is I'm going to make sure that each of my inputs only has one output. So -3 goes to 6. It doesn't go to anything else. So none of my x's are duplicated. That's to show it's a function is going from x to f of x. Now to be 1-to-1, we have to be able to go the other way. So that means I cannot have any duplicates on the right-hand side either. So 6 goes to a -3, and 6 is not included anywhere else in my table. Okay, so yes, that one is a function. Let's look at 21. So 21, I'm looking for any duplicates on my x column. There are no duplicates, so they all go to one output. And then I'm going to go to make sure it's 1-to-1. I have to make sure there's no duplicates on my right-hand column. And it looks like there are no oh, we do have a duplicate. 9 goes to 0, and then it looks like 9 goes to 2. So this is not 1-to-1. So 21 would be not 1 to 1. So you can't have duplicates in either column. Okay. The next questions I would like to look at are 23 and 25, 23, 25, and 27. So this is using our vertical and our horizontal line test. So 23 passes the vertical line test, but it does not pass the horizontal line test, right? Because every X value gives me the same Y value. So no. Let's look at 25. 25 looks like it passes the vertical line test, and it feels like it doesn't pass the vertical line test. It looks like it just starts to go up and down, but it's because there's an asymptote there and there's an asymptote there. So yes, it does, and it does pass the horizontal. And then 27 does pass the vertical, but it does not pass the horizontal, because look at, I can draw a line there and it goes through 2 points. I can draw a line here and it goes through 2 points. So this one is a no. So no, yes, and no. The next ones I'd like to look at are 29 and 31. Okay, and so 29 is the next one I'd like to look at. And 29 says, state whether each of the functions is 1-to-1. So my function is f of x equals a negative 3x plus 2. And if we go back to page 321 for a moment, at the bottom, there's a little blurb about 1-to-1 again. So it says, for a function f to have an inverse function, it must be 1-to-1. Okay. And then we can use a function is 1-to-1 if every horizontal line intersects the graph of f at most once. So, so if it's, so we could graph this function and we could tell, but we can see that if we put in any number for x, we will get a different number for y. And we can see that if we go to Desmos, we can put the graph in. Don't have my mouse here today, so it's working a little bit clunky. So if we go to Desmos and we put in y equals, and then we put in a negative 3x plus 2, we'll see that it does pass the vertical and the horizontal line test. We can also do this by hand. Okay. So we're going to actually find an inverse in the next couple of pieces. So we can see that it does vertically do that. We can also go to our gear and make the table and see that negative 2 goes to 8 and negative 2 will not go to any other number. And you can go the other way, that when y is a negative 1, so when y is a negative 1 down here, we could put the line at y equals a negative 1, and we would see that it never goes through another point. And so we can visually see that this is a one-to-one function. Now, the same can be said about number 31. So as far as we can check here, we don't know yet if it's one-to-one. So let's put it in. So 2x squared minus 3. So we can see that we can put in x equals 2, and we can see that we only go through the graph one time, right? And we could do that with any x, and it will only go through one time. But we can also see that if we put a line at y equals 3, that we go through the 2 points. We go through the graph twice. So if we put in 3, we go through the point. And you can see that here, if we make a table for our first function, we can see that, well, for instance, let's do this one at 2, because it comes, or 5, let's do 5, because you can see it in the table as well. So if I do the line at 5, you can see in the table that 5 as an output goes to a -2, and 5 as an output goes to a +2. So it does not pass the horizontal line test. So 29 is yes, and number 31 is a no. So I'm going to go back and share that on my paper with you all so you can see that. So 29 is yes. It is 1-to-1. And 31 was the function 2x squared minus 3, and no. It is not 1-to-1. Okay, so let's look at 33. 33 is a similar one. It's the function f of x equals a -2x cubed plus 4. And so we're going to go to Desmos and check this one out here. Okay, there we go. So we have a -2x to the third plus 4. So if we really zoom in, we'll see that these do not, it does pass the vertical line test, but we have to get very close. Whoops, we have to get very close to be able to see that, because when it's scrunched like this, it looks like it doesn't pass the horizontal line test. It looks like it passes the vertical, but it doesn't pass the horizontal, but it really does. And that's because it'd have to get very close here. So you have to keep zooming in to make this get so small that we can see that it does pass the vertical line test. Like I said, look at my x axis down here. My x's are so small because I'm trying to, oops, there we go. I'm trying to show you that. So we can make a table, and there's no way to see here unless we came up with numbers right around. So let's put in our table here. Let's say I put in a -0.0002. So I really want, yeah, x to be, so -0.0002. And then I'm going to put in a positive 0.00002. So it looks like it's at 4, but it's really not, because they're not giving enough decimal places here. So this one is kind of hard because it's hard to see that it, if it does or doesn't pass the line test. So it does. So 33 is a yes, it is 1-to-1. So let's go back to my paper, because we're on the next ones. Yes, it is. On the next ones, we are actually going to find the inverse. So on numbers 37 and 41. So we're going to start with 37. So 37 is the function f of x is equal to a negative 4x plus 1/5. Now, if you go to page, let's see here, 321. 321 gives us the steps. So we're going to start with our f of x function. We're going to remove the f of x and we're going to give that a y. And then we're going to rewrite the entire equation, and we're going to switch the y is now going to be called x and the x is going to be called y. Everything else will stay the same. Then we're going to solve for y again. So we end up with y on the right-hand side. That's how we create the inverse. And then all we do is we name it f to the negative 1 of x. That's the inverse of function of f. So we're going to go through the steps together. So I wrote my function out. There's my first step. My second step is I'm going to replace my f of x with a y. And this is 1/5. And then my third step is I'm switching my x and y. So y is now going to be x and x is now going to be y. All other pieces of the equation stays the same. And now my fourth step is I'm going to solve for y. So I'm going to solve for y. So that means I'm going to subtract 1/5 from both sides. And I circle the letter that I'm trying to solve for just so I can isolate it. And then I'm going to divide by a negative 4. So I'm going to take x and I'm going to divide by a negative 4. And then a negative 1/5 divided by a negative 4 is multiplying by the reciprocal of a negative 1/4. Oops. And then I have y. So dividing by 4 over 1 is the same as multiplying by 1/4. So we have a negative x over 4, and then a negative 1/5 times a negative 1/4 is a positive 1/20 equals y. So we can write this as a negative 1/4 x plus 1/20 equals y. And then our last step is just to write it as an inverse function. So this is the inverse function of x, and it equals a negative 1/4 x plus 1/20. That was super fun. So fun. Let's try another one. So let's do 41. So 41 says we have the g of x function, and it is a negative x squared plus 8. And the reason we can do this is because we're restricting x to be only greater than 0, because normally a quadratic function, which this is not, does not have an inverse. It's not 1-to-1, but we're only going to worry about the x's that are greater than 0. Okay, So to find the inverse, that's our step 1. Our step 2 is to write it as y equals a negative x squared plus 8. Step 3 is to replace y with x and replace x with y. And then step 4 is to solve for y. So to solve for y, the first thing we're going to do is get rid of this 8. We're going to subtract away the 8. So we have x minus 8 equals a negative y squared. We're going to divide by the negative 1. So that means we have a negative x plus 8 equals y squared. And then we're going to take the square root. So the square root of a negative x plus 8 equals y. And x must be greater than or equal to 0. That's going to be the same thing. Okay. And so then step 5 is always to rewrite it in function form. So we're going to say the inverse function of g is equal to the square root of a negative x plus 8, restricting that to x has to be greater than or equal to 0. Actually, less than or equal to 0. Because anything, this needs to be greater than 0, because negative x plus 8 needs to be greater than 0 on the inside. So flip that over, greater than or equal to negative 8. We divide by negative 1, then we flip our sign. So x next and 8. So x has to be less than or equal to 8. Yeah, so our restrictions are going to be x just has to be less than or equal to 8. That's 41. And you'll see if you check this in the back of the book, they like to write theirs as a square root of 8 minus x. And you can't read that because of my handwriting, 8 minus x. So either of those would suffice. Let's do a couple more. That was 41. Let's do 45. Once you get the hang of it, these are fun. I know you think I'm weird, and that's okay. F of x equals a negative 4x to the 5th plus 9. Okay, so we are going to write it as that's our first step. Our second step is to write it as y equals a negative 4x to the 5th plus 9. The third step, do you remember what it is? It is replacing y with x and then x with y. And then we're going to solve for y in step 4. I'm circling y. So I'm going to subtract 9 from both sides. And then I'm going to divide by negative 4. And then I'm going to take the 5th root, because the 5th root of y to the 5 leaves me with y. So the fifth root of x minus 9 over a negative 4. And then my last step is to write it as the inverse function of f. So it's the fifth root of x minus 9 over a negative 4. Is my final answer for that one. So that was 45. So how about 49? And you can graph all these using Desmos. So I'm going to make sure that it does say the graph. So I'm going to go through and we'll graph some of these once I do them by hand, just because I don't have my mouse, so it's easier to do it all at once. So let's look at 50. I said 49. So 49 is a g of x function that is x minus 1 squared. And we're only looking at when x is greater than or equal to 1, right? So that this is then becomes a one-to-one function. Okay, so that's step 1. Step 2 is, I'm going to write this as y equals. And then step 3, replacing y with x and x with y. And then step 4 is solve for y. Circle y. So to get at y, I have to undo the square first. So we're going to take the square root of x, and we're going to take the square root of y minus 1 squared. So the square root of root x, the square root of x equals y minus 1 because because the square root of the square cancels out. And now to solve for y, we have to add 1. So it's the square root of x plus 1. Make sure the plus 1 is outside of the square root. And then my fifth step is rewriting it as the inverse. So the inverse of g is equal to the square root of x plus 1 Okay, and then the last one I want to do is 53 in this section. But this here in this section, just for practice here. So 53, let's see if you can do this one. It's f of x equals 2x over x minus 1. 2x over x minus 1. This one's going to be tricky, isn't it? So that's the first step. The second step is replacing y here. So 2x over x minus 1. And then we're going to let x equal y and y equal x. And then we're going to solve for y. And to do that, we need to be able to combine our y's. So we could rewrite this as 2y times y minus 1 to the negative 1. Which means that y minus 1 would actually be in the denominator. And that's where it was. So can we actually find the inverse of this? I'm going to let you continue working for a moment and see if you can. Okay, so hopefully you figured out that that won't work because we can't distribute through because it says a -1 exponent. So what we could do is let's multiply both sides by y minus 1 to get this y out of the denominator for 1. So if we do that, it cancels on the left, and then we're going to get y minus 1 times x equals 2y. So we need to figure out a way to get all of our y's together. So let's distribute through this x. So we get x times y minus x equals 2y. And then we're trying to solve for y. So let's get all the y's to the left. Well, actually, let's just move all the y's to the right. So we'll have a negative x, and then we'll have 2y minus xy. We don't know what x is. That's okay, because we are solving for y. So because we want to solve for y, let's factor out the y. So we have y times 2 minus x. And then to solve for y, we could just divide by 2 minus x. 2 minus x. So negative x over 2 minus x. And if we factor out a negative from the top and the bottom here, we get a negative 1 times x over a negative 1 times a negative 2 plus x equals y. Then our negative 1 over negative 1 cancels. So we have a positive x in the numerator, and then these can just be flipped. So it can just be x minus 2 equals y. And so our step 5 is the inverse function of x is x over x minus 2. That was the trickiest of the tricky there. Okay, so I'm going to show you how you will do, how you are going to put these into Desmos here and check. So let's put this one in, y equals, y equals, and then we're going to have 2x divided by x minus 1. That's our first function. And I have to zoom out because I zoomed. I zoomed out so much before. And what I'm going to do is I'm going to just go to my, make a table, and then that way my magnifying glass shows up here on the left, and I can just do a zoom fit and it will correct it. And then I'm going to put the function that I think is the inverse function. So that is going to be y equals x divided by parentheses x minus 2. I think that's my inverse. And that's pretty cool looking for 53. Okay. Let's turn those off. And let's just make a note here. So let's go back and look at 49, for instance, here. So 49, it was, oops, y equals x minus 1 squared. Well, I gotta type it in a new line. Y equals x minus 1 squared. And then my inverse function, and remember, I'm only gonna worry about when x is bigger than or equal to 1, we said. So only to the 1 on. And then I'm gonna graph what I think is my inverse function that I created here for 49, which is the square root of x. So I have to go down and get the square root and put x, and then arrow, so you're out from underneath it, and then put plus 1. And you should be able to draw the line at y equals x, should go through those. So see where it cuts here through that point? That's how you know it makes it, that's a line of symmetry should also be always be at y equals x for every y equals x or y equals negative x for every function and its inverse. So I'm going to turn those three off for color right now. I'm going to go back up to, let's go back up to the 53. So there's 53 and its inverse. And then let's go up here. Let's do a note. This is number 53. And then let's do y equals a negative x. No. I mean y equals x. And you can see that it is also symmetric about that. Pretty cool, huh? It just looks symmetric in a little different way. Okay, so let's go back to what ones do we want to look at? So I would like to look at 65. So 65. So those ones on the ones that I'm assigning for this section down here in the book, 35 through 54, make sure that when you graph them, I want you to graph them in Desmos, and I want you to graph also with the line y equals x, because that shows the symmetry. Okay, so the next ones I'd like to look at are 65 and 67 and 69. So 65, it says a graph, we're giving a graph of a one-to-one function. You can see that. Draw the graph of the inverse function, copy the graph onto a piece of paper, and use the line y equals x to help sketch the inverse. State the domain and range of f and f of -1, the inverse. So on these, for the assignment, I'm assigning 66. I want you to give me the 4 points. You can make a table of the 4 coordinate points, right? And then that means your inverse is going to be the flip of your table. So let's go ahead and do that here for 65. For 65, my points are going to be a -3, -5, and then we have the point a -1 and -1, and then we have the point 1 and 2, and then we have the point 2 and 5. Okay, so that means that my inverse function of x, right? Sorry, my x and my inverse function of x, I should say. So my x's are now going to be my f of x from before. So I'm going to have a -5, a -1, a 2, and a 5. And my inverse function are going to be the x's from before. So a -3, a -1, a 1, and a 2. Right? So we're going to go and plot both of these in Desmos. So when you turn in your number 66, you're going to want to turn in a Desmos of your 4 points that you were given, and then the 4 points that will help you draw the inverse function. So let's go and do that in Desmos. This is now lesson 4.1. Yay. Okay. Okay, so let's go down here. Oh, something is graphed. Okay, now we can go down here. So let's draw, we have to go up and say we want to make a table. And in our table, we're going to put the point in -3, -5. And then we've got a -1, 1, and 2. And then our other y's are a -1, 2, and 5. Okay. And I'm going to hit my magnifying glass just so I can see out. So there's my 4 points in red. And now I'm going to make another table. So go up to the plus sign and click table. And this table, I'm going to put my points that we had on the paper. So a -5, a -1, 2, and 5. And my y's are a -3, a -1, 1, and 2. Okay. And they look kind of funny. So this is cool. I'm going to hit my magnifying glass so I can see them better. Okay, so there they are. And I'm going to just zoom out a little bit so we can see all the reds and all, there we go, all the reds and all of the blacks. And now I'm going to go up and just turn on my y equals x line so you can see that they are symmetric from one another. So these two are symmetric, evenly spaced from the y equals x. These two are evenly spaced. Those, it actually goes through that point. That's pretty cool. And there's the other two. That's pretty cool. Okay. Let's look at 67 and 69. So we're going to need our book for this one. So I'm going to show you here. So 67 and 69 are using this table. Okay, so it says, by referring to the function, evaluate the following. So 67 says, evaluate the inverse at 1. So I'm going to rewrite this table. So it might help you to rewrite the table here. This is going to be 67. So I'm going to just rewrite the table. And we have -2, -1, 0, 1, and 2. And then 1, 2, 0, -1, and 2. Oops, -2 down here. And so I'm gonna then do x in my inverse function of x. I'm just going to rewrite it. So then I can really it'll help me better. So now these are all of my x's over here. So 1, 2, 0, -1, and -2. And these are all of my outputs, -2, -1, 0, 1, and 2. Okay, so 67 says the inverse function at 1. So I'm going to the table of the inverse function, that's table 2 over here, and I'm going to put 1 in. So when I put 1 in, I get a -2. So let's do 68 together just so we can see. So 68 says the inverse function at 2. So the inverse function of 2. So I'm going to go to the inverse function. I'm going to put 2 in and I get a -1. You're going to do number 70. So we're going to do 69 together. 69 is trickier. It's the inverse function of the inverse function of a -2. So we first have to find the inverse function at a -2. So the inverse function is table 2. And so at a -2, we get 2. And then that has to go into the inverse function again. So then we go to the inverse function again, put in 2, and we get a -1. Those are kind of tricky. So you get to do number 70 for homework. And the last problem that I would like to look at is number 77 on page 330. And it says, in economics, the demand function gives the price P as a function of the quantity Q. And it looks like as the quantity of demand goes down, the price is going to be more expensive. No, as the quantity gets bigger, yeah, as the quantity goes down, the demand gets okay, this is the demand function. So right, so as the price quantity goes down, drives the price up, because this is opposite here. Let's just draw it in. I want to show you in Desmos. Y equals 100 minus 0.1 x. And I'm going to go up and turn this other thing off here. Okay. And we can't see it, so y equals, did I put it in right? Y equals 0.1 x. Okay. So we have to adjust it. So I'm going to go and create the table so I can do my magnifying glass, and there we go. Okay. So here is our, I'm just zooming way out. Okay. So as you can see, with your quantity goes up, it's driving the price down. So the more you have, the price goes down. Now, that's the thinking of the selling of the product. If you're buying a product, right, the fewer the products that are out there, the price goes up. That's what's happening right now with our economy, is that because they can't get some products in, and they can't make cars, or they can't can't find ham at the grocery store or whatever, it drives the price up because people are willing to pay more because they really want to get the product. So it depends on how you're thinking about it. So in this problem here, it's so back to the equation, let's just write it out here, 77. As the quantity increases, the price goes down. Okay. So it says, however, mathematicians tend to think of the price as the input variable and the quantity as the output variable. How can you take this example of a demand function and express Q as a function of P? So we're basically doing the inverse. So we're already in step 2. And step 3 means we're going to replace Q with P, and we're going to replace P with Q and Q with P. And then step 4 is we're going to solve for P, because they wanted us to find Q as a function of P. Okay, so we're solving for P. So we're going to subtract 100 first. And then we're going to divide by the negative 0.1. So we're going to have Q minus 100 over negative 0.1 equals P. So that's one way you can write it. We can also break this apart and say Q over a negative 0.1 minus 100 over a negative 0.1 equals P. And then we can find out what both of these are in Desmos to rewrite it a little bit here. Actually, let's do it on our calculator. So we can say 1 and divide it by 0.1 and we get 10. So this is really a negative 10q, and this is a negative over a negative, so it's a positive, and then we'll do 100 divided by 0.1, and that's 1,000 equals p. So now you've got it in integers, the same thing written in integers. So then our fifth way is we're going to write the function of p, where q is the function of p where q is the input. So it's a negative 10q plus 1,000. So the price is dictated by the quantity. So as the quantity increases, it drives the price down. So we can go and put this function now into Desmos and see what it looks like. So we can do y equals, and we'll put a negative 10x plus 1,000. Because that's such a large number, we need to put in our table, and then, okay, so let's zoom way out. It's hard to see that these are inverse functions of each other because let's just do y equals x there. So it's hard because the scaling is off so much that it doesn't appear that they are, but they really are. So we can see here that they are symmetric from each other. Okay. That is the end of 4.1. Woo, that was a lot. Catch me back for 4.2.